Okay, now we're here. All right. We are starting quite late today. But yeah, we'll just go ahead and hop on in. I was not able to get to my cards today, unfortunately. Hopefully maybe I'll grab those after. Okay. Okay, so for non-rational functions, you're looking for, as x increases to infinity, both positive and negative, or rather, for positive, well, as x approaches infinity, you're looking for a y value that approaches some number. Yeah, so taking the limit of infinity is like a good option. Let's see. Yep. Okay. Yep. Perfect. Vertical asymptotes is when x is a particular number, y, or sorry. Yeah, as when x is a particular number, y approaches infinity. So you're looking for, so it's like hard to say. I guess you should also look for like instances when the denominator is approaching 0, because you know that's going to cause an infinite y to approach infinity. So I guess you'd look for, even in non-rational functions, like if we have a square root or pi, then we'd be in that situation. As for other functions, I hopefully there's something that describes when it's not in the case you have a denominator. Okay. Identify points where function is undefined or discontinuous. Okay. Okay. Yeah, I think that's reasonable. For a function to be continuous at a point, so for a given variable c or f of c has to exist. Taking the limit of c has to exist, and the result of taking the limit to c has to equal f of c. Okay. Bounded function is one wherein the range of, or for like a given domain, negative to positive infinity, the output or range is bounded, so it is within the bounds of some two numbers, and we can be upper bounded and lower bounded. Yep. Okay. Sweet. Okay, I'm gonna grab the calculus. I'm excited to finish calculus because I want to start statistics. Okay. So let's, actually we probably just want this. Then we'll increase this here. No, I don't know how good that is, but here we are. Okay. Maybe even one more. Okay. Okay. Oh, I wanted to... okay. I wanted to edit this so it was better. Okay, so this is part B. Identify horizontal and vertical asymptotes. So we have neither in this situation. So there's no vertical asymptotes, so the function is continuous and remains finite for all finite x. Okay, this is actually a good definition. There's no horizontal asymptote because... okay, yeah. So I'm gonna... okay, Um, X approaches negative or positive infinity Y also, oh my heavens, also approaches negative and positive infinity. Okay. As to say, as we approach infinities, we don't end up at a finite y. So I'm going to see if this is better. No. Okay. I want to try to find... Okay, I probably won't be able to do it. Equation. Do. Oh, okay. So maybe this, I see. So the weakness of this argument is that, or the weakness of this one is that I say that it approaches positive negative infinity as x approaches positive negative infinity, y also approaches positive and negative infinity, but we're dealing with a sine function, and sine oscillates between 0 and 1. So, okay. Okay, okay, so I'm comfortable with where we're at there. I think a limit analysis would be a little bit better. Actually, no. Let's adjust that to include that. Let's see. Okay. It is continuous. Continuous because as x approaches the piecewise transition point. Piecewise? What the? Piecewise transition point. As it because the limit taken from either direction on the piecewise transition point is equal. Is that correct? Equal is equal and and is the same as pi f of pi. Okay, I think that's technically correct because remember when we had continuity, we're talking about like for a given value c, f of c has to exist. Taking the limit of c has to exist, and f of c and taking the limit of c both have to be equal. So I think that's additionally f of exists. Okay. Oscillates. Oh yeah. SC oscillates. Okay. Perfect. Okay, and this one I'm going to just knock out of the park. Well, at least I hope. Okay. The mean value theorem states the mean value theorem. Oh. I know the conditions for the mean value theorem, but I feel like my definition is a little verbose. Okay. Well, states that there is a tangent tangent line that matches the cotangent line that can be drawn through 2 pi and 3 pi. 3 pi matches, we'll say, is parallel to. Okay. Too many L's. Okay. This is the case because the function matches or meets the following criteria. It is differentiable on an open interval. 2 pi, 3 pi, and it is continuous on a closed interval. 2 pi, 3 pi. Oh, shoot. Backslash. Perfect. Okay. I think that's a killer. Exists. Oh, there is a tangent line. That's fine. Do. Oh, shoot. I said cotangent line, not the secant line. Oh, the secant. No. No secant line. Wait a second. There's a jump discontinuity at 2 pi. Okay, so I asked about my answer, right? And then Grok was saying that there was a discontinuity at 2 pi, but I think it just got like mixed up. So okay. Okay, so it was good. But looks like I just needed like a little bit more meat. Anyway, Grok was mixed up a little bit on 2 pi. It's saying that there was a just jump discontinuity there, but this is a continuous function. And so we're good there. I do want to refine my definition. So when you're interacting with a particular domain of knowledge, it's important to understand what the important things, but the important like meta things are within a particular domain. And so I haven't, interacted with mathematics in a long, long time. But one thing that's clear here, and for each of these that I've interacted with, is that Grok is wanting me to be really precise. So even earlier, I said criteria, but conditions is the preferred term for mathematical writing. Additionally, I said matches in parentheses is parallel to, and like it is the case, but it's not precise, right? And so, yeah. Yeah, so I guess that's to say, that's good to know. Okay, so I'm going to refine my definition. So we're going to be ending here soon, but I'm going to refine my definition for the mean value theorem for next time. And then we're going to hop on to the next question. And I feel like these next questions will, these will be probably quicker. Yeah, we'll see. Cool. I will see you guys next time.